why can't we land things on Mars like we do the old-fashioned way with parachutes? Well, somebody said, well, you can a certain amount like they did with a certain amount, but you still have the problem with let me fix this. You still have problems with the difference in the density of the air and the chemical makeup, the makeup of the atmosphere versus Earth and all that. So I went through and did a little calculation and said, well, they're right. You know, use one big parachute. You cannot technically land something on Mars. Now, in doing that, I said, well, what's a good way to compensate for the speed of the object when it lands on the surface? Now, we on Earth have been doing this for hundreds of years. We got a good atmosphere for that, so we've done it since, I don't know, a couple hundred years ago. Safely, something jump out of a plane can land safely on Earth with just the help of a parachute. Now, the density of the air on Earth is a lot more dense than it is on Mars, so you have to compensate for the downward speed. And the way I came up with it is called what I call sky climber. Now, the sky climber is a device basically that is there's a long tether from the parachute. At the bottom of the parachute is the payload you're going to drop. And the payload you're going to successfully land on Mars. In doing that, to compensate for the downward speed, the object has to move up towards the parachute to compensate for the downward speed. It's all relative. Let's say you're going at 70 kilometers an hour, then that speed would have to be compensated, or else you're going to hit pretty hard on Mars. So the device I came up with, first we'll go through and use some, talk about, I thought I was well prepared. You haven't done an HDMI hookup yet. That's all right, we'll get to this. We'll talk about the different types of landers and rovers that have been successfully landed on Mars. They all were done with rocket engines. So for the last 50 years, we've used rocket engines on Earth and on Mars. But when the Apollo landers came in and came back from Mars, they used parachutes to land in the ocean safely. They didn't use thrusters, they used parachutes. So when we talk about landing on Mars, a good way to compensate for that, first of all, we'll explain some of the past theories behind it. We had Viking, had rocket engines underneath, very successful program for the time that it landed on Mars. Then we have the Pathfinder, the airbags drop, use thrusters, rocket thrusters, to slow this descent down, and drops the airbags. It bounces around a little bit and settles. Then we got Curiosity, not Curiosity, but the MER rovers, Opportunity and Spirit. They came down, thrusters, again, airbag. You can see it, but it's right down there. They let it go and it bounced around for a while and then finally settled. Now, well, the next thing bigger is the Curiosity, which is a lot bigger. As mentioned, it weighed about 1 ton when it was finished with. 1 metric ton. So they came up with a device called the sky crane, which basically came out and held, the mass of the sky crane. They had transport from Earth to Mars. The rocket engines, they had transport from Earth to Mars. And it successfully lowered Curiosity rover into safe landing. And then it took off. Okay. Now that we discussed all that, I thought, well, there must be a better way to do this. Kind of without, I don't want to, I know some of you are rocket engineers and all that, without the use of rockets. And with payloads, Curiosity size are lower, 1 metric ton lower. We're going to need to drop a lot of cargo on Mars and do it very efficiently. And do it because the more mass we transport off the planet, the more it's going to cost you. And so if we take something as simple as parachutes and a device, an electric device that actually compensates for its downward speed by actually going up the tether line towards the parachute. You're transferring the relative speed downward. You're transferring that. You're actually lowering the speed at impact down. So this is basically how it works. It comes in about 1920 meters per second, about 43 miles per hour. I mean, no, it's coming in pretty fast. About 43. After the use of 3 large parachutes, equivalent in size to what the space shuttle external solid boost, rocket boosters use when they landed in the ocean. Now, its relative speed before it hits the ground. Now, if it continues on down, it's going to crash into the surface about the same speed, using 3 parachutes, 3 large parachutes. Now, if you're compensating for your downward speed by actually going up a tether line towards the parachute, you're lowering your relative velocity down. You're doing 2 things. You're also, the parachutes are actually also coming towards you. You're putting more of a load on the parachutes. So you're creating more resistance of the parachutes to go any faster because you're actually increasing its speed, which it will counteract. So you're slowing the speed of the parachute down. And you can control all this. Control all of it by if you accelerate up, you're accelerating up and you're changing the speed. Your control factor is an electric winding device or some kind of a device that actually accelerates the load up, the payload up towards the parachute. Now you got an electric engine on here, let's say Curiosity size, somewhere between 60 kilowatts per hour or 85 kilowatts per hour. I'm using that on purpose because Tesla has, the Tesla S has a 60 and 85 kilowatt per hour electric engine. Very lightweight compared to the internal combustion engine. And you're using a storage device. Now Tesla, for example, has a 900-pound battery. That's to go 250 miles Now, you're only using about up to 10 seconds of stored energy. You don't have to go 900 miles. You just have to use that. But you'll have to put in with that, you have to put supercapacitors that actually can dump the amount of energy you need more quickly. But that's workable. And the mass of the battery would be somewhere in around 2 kilograms. That's 2 kilograms of stored energy that you use at the very last to slow the speed of the parachute down to slow enough to be able to actually get a soft landing. And that's all control. All control. Once it comes down to a certain level, it knows how fast it's going relative to the surface. So that it compensates, you know, the density of Mars changes. And it changes from night to day, and you know, depends on you know, dust storms and all that. So we don't really know when we send it what you're going to run into there. So they always have to take more fuel and over-calculate and all that. But with this, you have a minimum amount of mass you're transporting from Earth to Mars. And that's a big factor. And the minimum amount of mass is you're using that to drop, you know, all your equipment, rovers. Once you get good science and everything else behind it, and you know, all the payloads that you need to put on Mars, very reasonably priced. Instead of hauling huge amount of fuel and a device like the sky crane, you know, that's mass, to Mars, to make sure you got a soft landing. Now, those things are inherently, they got a lot more, I'm not a rocket scientist, but they got a lot more, you know, involved thinking and doing that, to do it right. But with this, it would be a lot simpler method to do it. It's there to help humans explore Mars. It will be there to help them add an extra layer of security if something goes wrong and they have a redundant object, something that they can use in case something goes wrong and they're not actually, so that could be used as a backup for a human flight to Mars. Now, I did a little animation. I did a little animation. I want to show you. And it will basically show you about what I'm talking about. I've done tests on this, on Earth. That's it. It's coming through the atmosphere. You got a drag chute here, and I had a little bit extra. I had little winglets that pop out to give you direction. You're not going to get much lift, but you'll be able to be directed to your target. Then it goes into a free fall, and three parachutes come out. The size. No, I'm talking about this is if this was done with Curiosity rover. This would be about the size that they use on the Space Shuttle external tanks when they come down and drop into the ocean. So it's now let's stop the rover. The rover it's through a tether line, and that rover is now falling underneath the parachute and the capsule. And now, right in here, the rover is actually starting to accelerate up that tether line. It's changing its relative velocity downward by going up the tether line. And in doing that, it's pulling on the parachutes. The parachutes wants to go faster. Parachutes want to go faster, they put up more of a resistance because now there's more dense air that they have to go through. So it slows the descent down. And then, if all goes well, it lands safely out of the way. And I'll show you some of the tests I've done. This is a little winding device here, and I had a string up there. And what it is it's going up the tether line towards the string. So basically, it's just a practice run to get this working right. Then I attached it to a parachute. There it's attached to a parachute. Now the parachute, and that's in the free fall. Now, when I purposely did a test on the amount of weight that I needed to drop it with, to have it go a little faster than what it should be. The idea is to prove that once it drops, it's actually going up the tether line towards the parachute. It's going up the parachute, and it's slowing its relative speed down so it can land safely. And, it's just, why can't we do that on Mars? Now, yes, you've got density difference, and all that other stuff. And it's to me, I don't understand why we can't. Now NASA is finally come around and saying, well, hey, they just did some tests. And they said, well, maybe we can use more than one parachute. Maybe we can use bigger parachutes to help slow some of this down so that we don't have to take so much fuel to Mars. Why, and so now they're coming around to using 3 parachutes or more. I'm not sure what their plans are. But, it took them a long time to think that, and humans were doing that for over 200 years. Anyway, that's all I got. Thanks.
So the airbags in the Skytrain system were designed to accommodate a horizontal velocity. How does this account for that?
The horizontal velocity?
Yes.
Yeah, this would there have to be some kind of way to compensate for that. And so you're right, but it's workable. I came up with an idea of using, but it's a thing that's workable. It's not a.
Because you can have the winds at 200 miles an hour. It's not enough to be a problem. You won't hardly notice them if you're walking on the surface. But with a parachute or a balloon or something, you're fully involved in what the air is doing.
You're going to be drifting at the wind speed.
Yeah, you're going to be drifting.
So you can be drifting at 200 miles an hour.
You also have this device right here. As you're coming down, you're right here. Oh, I guess so. See, I put little winglets on that.
How does that arrest your horizontal velocity?
Well, you would use, as an airplane would use, to slow
A
down.
little louder?
Huh?
I can't hear you speaking.
Oh, you use it like an airplane would do to slow the velocity down.
So it's not the drag on the spacecraft.
Not
that's
the
gonna
drag
be-
on the spaceship, no.
It's
But
going to be
you-
the push on the parachute. that's
Yeah,
gonna be
but,
pushing.
you know, you probably wouldn't need some kind of a reverse thrusters like an airplane would use. And
So
you would
you
have
do-
to compensate for that, you're right.
So you
Yes.
do need a little bit of rocketry at the very end.
What?
So a little bit of rocketry at the very last few
But
seconds.
yeah, you probably maybe use some kind of thrusters. It's not, you know, totally independent of thrusters, yeah.
But that will give you a lot more out of one.
But the idea is that you're slowing down your relative speed down. And yes, you're right, it does need, you know, yeah. right.
Is there, compared to the current, like the sky crane, the parachute they used before the sky crane, would the parachute need to be bigger to provide more air resistance as you reel the line in or not?
Yeah, well, the parachute has to be bigger because the air is so thin. So the air is real thin, and the parachute's bigger, but, you know, it's still not going to slow it down to where it's safe to land without some kind of system to adjust for.
Yeah, for robots, up to about a ton or so, that probably will still work. But even now, they're talking about heavier robots, and they're trying to develop that balloon type thing.
Yeah.
But for manned landings, with you need a parachute with 50 times the area.
Yeah.
And besides that, the parachute is expendable, and we don't want expendable vehicles. So it kind of rolls out any of
Everything
that
you
stuff.
land on Mars should be reusable.
Right.
Parachute maybe.
But for a robot, it doesn't matter. The robot is one-time use, so the parachute can be a one-time use. That's not a
Yeah.
problem at all.
Yeah.
You're making many trips up and down.
Okay,
Right.
go ahead.
Yeah.
Sorry.
I can see you arresting the horizontal velocity, and certainly the concept of reeling up is cogent. You can see how that works. But
Yeah.
the question that I have is and certainly if you begin to put more, or if you pull down on a parachute more, there's going to be an initial elasticity, there's going to be a spreading out, and there's going to be a
Oh,
resistance. But there will be a recontraction, and you're going to do.
Well, the
Wait,
way-
let me finish, please. My question is do you have hard data as to the speed changes in the parachute? Because I agree, I mean, there would be an initial one, but the parachute's going to go back to its original shape, and your descent is going to be at the same speed as it was before the load was put on it.
Yeah, it needs to be tested.
Okay, so
More.
you're waiting for hard data.
Yeah,
Okay,
hard
thank
data.
you. No,
It's not like hard
I'm
data.
just asking for the
Yeah.
data, is all. Thank you.
Yeah, and the first question, what was that again? You said, how do you compensate for?
No, you've already stated that you would be using thrusters to handle the horizontal.
Yeah.
And then
I'm trying to get out of that, but yes, right now, but the thrusters would use a lot less energy than what you use to slow it down.
I'm not.
Okay.